Welcome back to another exciting Q&A episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I'm your host for this episode, Heidi Campo, filling in for Andrew Dunkley. Joining me today is Professor Fred Watson, astronomer at large. How are you today, Fred?
I'm fine, thanks. I'm still at large, which is always good. No, very well, thank you, Heidi. And I hope you are too. How's the weather doing in Houston? You were concerned about the heat and the rain and...
Oh, it's been beautiful. Last couple of days have really been nice. I actually sat out on that patio. We have a little patio in our backyard. Had a little sparkling water, watched my dog play in the yard, and it was pretty nice. I think they sprayed for the mosquitoes recently, so those have calmed down a little bit.
Yeah, that's right.
And no hurricanes yet, which is, let's knock on wood, because that's my favorite part right now is not having hurricanes.
As it would be. Yeah.
All right. Good. Well, we have our first question today is from Greg from Minnesota, also a hurricane-free zone. You're safe from the hurricanes, Greg. I hope you're enjoying not having them in Minnesota. And Greg says, "G'day, Fred, and howdy, Heidi. I'm Greg from Minnesota, USA. And I have a question about photons and quantum energy levels. We know that energy is quantized, that therefore photons can only exist at certain discrete energy levels. We also know that space is expanding and that traveling through the expanding space saps energy from the traveling photons. What happens when a photon has been traveling so long, so far, that the energy it carries drops below the minimum allowed quantum energy level? Does it disappear? I love the podcast, and I'm looking forward to your answer."
Yeah, I think this is a great question, and it certainly had me scratching my head, Heidi. It sent me to the Fermi Lab, which, of course, is one of the key nuclear physics facilities in your country. They have a marvelous website called Physics Questions People Ask Fermi Lab. And I think the nuances of the answer are probably best expressed by the account that I've got in front of me, which is by one of their PhD physicists. In fact, Lila is the editor of the Office of Public Affairs, Lila Belcora, who says, and I think this puts it a little bit into perspective, let's put aside the idea of a photon losing energy in transit as an explanation for redshift. A photon doesn't lose energy unless it collides with a particle. Photons can scatter off interstellar electrons, for example. Photons carry energy, but they don't lose energy just because they travel. And this is the key to it, as Lila says. The key to understanding the dilemma of a redshifted photon, and that's to say one that's traveling through space, through expanding space, and so the space has expanded, the photon has been redshifted, it's got a lower energy level. The key to understanding that dilemma is that not all observers will measure the same energy of the photon. Let's say an observer is traveling with a star or galaxy and sees a photon in the yellow portion of the spectrum. An observer who is moving with respect to the star, and it doesn't matter if it's a star or the observer moving away, sees the same photon in the red part of the spectrum. That's okay. It doesn't violate the principle of conservation of energy because they make their measurements in different reference frames. So that's a complicated way of saying that photon energy is quantized, but it's never going to reach a stage when it falls below the minimum allowed quantum energy level. So it doesn't disappear. I hope, Greg, that explains the answer to your question. It's one that had me scratching my head for quite a while, and I thought that Lila's comment in the Fermilab website actually put it very well. If you want to follow up on that, it's pretty easy to find. Just look for Inquiring Minds, Physics Questions People Ask Fermilab, and have a look at it. It's very nicely written, and perhaps lays to rest some of the things that we do think of. We take for granted that photons are losing energy because they get redshifted, but they're only redshifted in our frame of reference. That's the interesting nuance to this question.
Oh, that's that I'm still wrapping my head around that one. That's so interesting. Whenever you go anywhere close to the world of quantum, it's just everything changes. All the rules change.
That's right, they do. A lot of it's completely counterintuitive, but it seems to work. You know, what we hear about in quantum physics, for example, entanglement. This idea that you can bring two particles together and they'll behave as one particle, even though you then separate them, they still think they're one particle. That is quite counterintuitive.
Yeah, there was a cute little movie that came out recently. It had Chris Pratt and, oh my gosh, everyone's going to make fun of me because I can't remember the girl's name. She's the girl who's from Stranger Things. she's very famous right now. But the whole premise was once particles touch, then they're never separated, and it was kind of a love story type thing. It was kind of cute. But yeah, once particles have touched, you never lose that connection. It was kind of cute. Well, our next question is from Russell, and this is an audio question. So I'm going to give Fred a second to cue that up, and then we are going to play that question for you guys to listen to now, and then Fred is going to answer that question for all of you. So here is Russell's question.
Hello, Fred and Andrew. This is Russell from Reading in the UK. There's been a recent suggestion that the universe is inside a black hole, but my understanding is that the event horizon of a black hole is not a thin membrane, but extends all the way down to the singularity. This means that light and everything else can only travel in one direction, which is towards the singularity. So it would be immediately obvious if we were inside a black hole, because you could only see in one direction, which is away from the singularity. What have I missed? Thanks for the great show.
So Russell's asking what he missed. And I don't think he missed anything, actually, because, the idea of the universe being a black hole, or the whole universe being within a black hole, is extremely speculative and really does not have the imprimatur of the scientific community, and that's just another way of saying nobody believes it. Questions like that I think are very good ones, because intuitively you would expect that to be the case. Now, just pursuing this a bit further, the people who work on theories that perhaps the universe is inside a black hole, they are not stupid. So they're people who have great insights in physics. And so I suspect their thinking is along the lines that if we're in a black hole, we're not just within the event horizon. We may well be within the singularity, because a black hole is a singularity. It's a point where physics breaks down. It's basically a point of zero dimensions and infinite density. Are we inside that? If so, that would mean all bets are off. We wouldn't have any idea how physics worked, but the universe seems to be pretty well behaved, and we can understand it from the physical laws that we have. If we're inside the event horizon, then we should see evidence somewhere of the black hole itself, like the kind of thing that Russell suggested, like going only one way. We see no evidence whatsoever of that kind of thing. The universe, as far as we can tell, is isotropic. That basically means it's the same in all directions, give or take bit of structure that we find from galaxies, nevertheless, it's more or less the same in all directions. And that seems to fly in the face of the idea of a black hole universe. So I think Russell's asking what he's missing. I don't think he's missing anything. I think he's facing the same sort of challenge as people who propose this idea have to face. There's quite a lot of material on this topic on the web, not too hard to find. It might be worth a poke around, Russell. Nice to hear your accent coming from Reading down there. I know Reading not that well, but I do know it in the south of England. There you are.
That was a good question. I recently rewatched the movie Oppenheimer, and they brought up the with quantum physics and everything. They said something about anybody can do math, but for the real theory, it's like, can you hear the music? Can you see what can't be seen? And I think that's really, we do get a lot of people writing in with questions who think like that. We have a lot of very creative, very scientific-minded people who are, I mean, you guys all should be scientists, because some of the questions we get are very, very deep scientific thoughts.
Time to take a break from the show to tell you about our sponsor, Incogni, INCOGNI. I'll give you a special URL shortly so you can get it 60% off Incogni as a Space Nuts listener. And if you're tired of your personal information being spread across the internet and getting hammered by all these spam emails and spam texts and spam phone calls, then Incogni is the answer. It's a privacy tool that scrubs your sensitive data from over 180 data broker sites automatically. Whether it's your phone number, your home address, your browsing habits, your email address, whatever personal information is online is cannon fodder for these people. Incogni uses legal rights like GDPR and CCPA to get your data removed. You sign up, and Incogni does the rest, sending removal requests and tracking progress on your dashboard. It's fast, it's secure, it comes with a 30-day money-back guarantee. It's an inexpensive way of getting yourself cleaned up so that you don't get spammed. And who knows what else is happening to your data online. So go to incogni.com/spacenuts and use the code spacenuts for 60% off right now. Incogni.com/spacenuts, 60% off. And don't forget the code word spacenuts at the checkout. Incogni.com/spacenuts. Now back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Let's bring that to our next question, which is going to be Paul from Melbourne, Australia. He says, quick question. Hello, Heidi, Fred, and Andrew. When Isaac Newton noticed an apple falling from the tree, did the planet Earth ever so slightly get tugged toward the apple as it fell to the ground? Thanks. Love the show. That's Paul from Melbourne with another deep, thoughtful question.
Yeah. I think the answer is yes as well. When we think of and this is the Newton idea that gravity was a force, Einstein told us it's actually something different from that. It's a distortion of space. But just sticking with Newton's idea for the moment, the mutual attraction between the apple and the Earth goes both ways. The gravity of the apple would also be attracting the Earth, but not to any significant degree, of course, because of the ratio of their masses is so high. But there would be an infinitesimal nudge of the Earth up towards the apple. I think so. The answer is yes. It's a great question, Paul. Paul might also be interested to know that the apple tree is still there. That Newton is reported to have seen the apple falling down. The place where he worked out his theory of gravity. He was actually in quarantine from Cambridge in a place called Lincolnshire, which is further north than Cambridge, when he lived in the family manor, because they were a very well-heeled family. But his bedroom window overlooked this apple tree in the orchard. And so maybe it was looking out of his bedroom window that he saw apples falling and made him think about this force that pulls stuff down to the ground, which is the same force that keeps the Earth in its orbit around the sun and keeps the moon in orbit around the Earth. So it's nice that the apple tree is still there. It's got a fence around it now, so nobody cuts it down.
Does it still produce fruit?
I don't know the answer to that, Heidi. It might just be a little bit elderly because that was all in the 1680s when that was happening. So 1660s, I beg your pardon, when that was happening.
Well, that would be pretty crazy. I'm just thinking of the capitalist thought with that. It's like, okay, we're going to sell Newton apple juice, and it's going to be from this tree, and we're going to brand it as this is what genius, the genius apple juice.
I think you're right on the money there, and that's probably the fact that it doesn't produce apples anymore is why that hasn't happened.
Yeah, unfortunately.
Let's take a break from the show to tell you about our sponsor, NordVPN. And we're very proud to have partnered with NordVPN so that we can get you more secure online, no matter what you do, where you are, or how you do it. Now, if you sign up for a 2-year NordVPN plan using the code word SpaceNuts, you'll receive 4 extra months absolutely free. That's 28 months of top-tier VPN protection at a fraction of the cost. With NordVPN, what you get is access to over 7,700 servers worldwide, ultra-fast connections, advanced features like Threat Protection Pro and MeshNet, and secure usage for up to 10 devices simultaneously. So you're pretty well covered, you have to admit. Now, this is a great opportunity, and if you'd like to take advantage of it, visit nordvpn.com/spacenuts to claim your exclusive offer today. And remember, with NordVPN's 30-day money-back guarantee, it's risk-free. It's a great investment, a small price to pay for your online security and privacy. Stay secure, stay connected, and keep exploring the cosmos with confidence. nordvpn.com/spacenuts, nordvpn.com/spacenuts, and don't forget the code word SpaceNuts at the checkout. Now, back to the show.
3, 2, 1.
Space Nuts.
All right. Well, our very last question today is from Mikey, and this is also another audio question. So I'm going to give Fred a chance to cue that up, and then we are going to play that for all of you to hear Mikey's question, and then Fred will answer that. So I'm going to go ahead and play that now.
Hey, Fred and Andrew. I hope you're doing well. This is Mikey once again from Illinois. I wanted to talk about the European Space Agency's solar orbiter. And I know that it was the first spacecraft to ever take images of the north and south pole of the sun, which is a huge thing because every time we've taken any photos, it's been from the ecliptic plane. And that got me thinking, was that spacecraft, or is that spacecraft the only thing to ever make that orbit that wasn't in the ecliptic plane, man-made or not? Is there anything else in our solar system that takes that kind of orbit? Or was that spacecraft the only thing ever in our solar system to orbit outside of the ecliptic plane? That's just, it's hurting my head thinking about that. Hopefully that question makes sense to you guys, and I can't wait to hear the answer.
Yeah, I can't wait to hear the answer either. This is a really good question with quite a thought-provoking idea to it. I've never thought of that as well. We don't really often see pictures of the top and bottom of the celestial bodies.
Yes, that's right. So the answer to Mikey's question, which is, does anything in the solar system orbit outside the ecliptic plane being the plane in which the planets and most of the asteroids orbit the sun? And the answer is yes, comets do. So comets come into the inner solar system in their very elongated orbits from pretty well all angles. And so they sometimes come from the, above the ecliptic plane, sometimes from below it. And that's why we think that the source of comets is actually a spherical shell of cometary material, because they do come in from all angles. So it's stands to reason that their origin, if there is a cloud of these things outside the domain of the planets, as we think there is, then it would be spherical. And that we call it the Oort cloud. It was Jan Oort, a great Dutch astronomer, who postulated that. So comets do. They're natural objects that do orbit well outside the plane of the ecliptic. But in terms of spacecraft, no. There are spacecraft that are above and below the ecliptic. In fact, Voyager 2 is the classic example. That is heading out of the solar system, well below the plane of the ecliptic. It's well to the south of the ecliptic plane, which is why the only radio telescope in the world that can communicate with it is here in Australia, because we see that part of the sky. But you're absolutely right, Mikey, that this is the first time a spacecraft has seen the poles of the sun. And it's actually only, at the moment, I think the tilt of the spacecraft's orbit to the ecliptic is only about 15 degrees. It's not very high, but it's still enough to be able to see over the top of the sun. It's the bottom of the sun, if we put it that way, because I think it's the South Polar region that's been imaged. But they are, ESA, the European Space Agency, have plans to increase the tilt of the orbit. So we'll have a much better view of the sun's south pole. The process of changing the angle of an orbit is actually quite expensive in terms of fuel. It's not a straightforward thing to do. So it's it's a very ambitious thing to do for the operators and the mission controllers for the solar orbiter spacecraft to be able to do that. It's obviously been built into the mission. The spacecraft actually went into orbit around the sun in 2020, so it's been working for 5 years, and I think the mission profile has this steady increase of the orbital angle. What's perhaps even more interesting than that is what they found at the sun's poles, the South Pole, and that is a confusion of magnetic fields. The sun's magnetism is very bizarre, unlike the Earth, where the magnetic fields are strongest around the poles of the Earth. It's the opposite way around on the sun, at least at the moment. It's something that changes with the sun's 11-year cycle. So at the moment, the sun's magnetic activity is really mostly around its equator rather than at the poles. And there's a jumble of magnetic fields been discovered at the poles, which is probably due to the fact that at the peak of the sun's activity, which is where we are now, the magnetic field of the sun actually switches from north to south. So that might be why we're seeing this confusion at the pole of the sun. So yeah, great question, and such an interesting spacecraft as well. I once again encourage you to get online and check out ESA's solar orbiter. There's some fabulous stuff on the web with many, many images of what's happening near the sun's poles.
Yeah, I think I was reading about that one recently too. And yeah, I mean, really, this industry is picking up. There's so much happening every day. It's hard to keep track of. But we mentioned this a little bit before we started recording. But Fred, you subscribe to so many news resources, and it's your morning routine. I've got one question for you about how much time do you dedicate a morning to reading through the space news and updating yourself to stay up to date. Can you walk us through a little bit of what that routine looks like for people who want to, who kind of aspire to be a little bit more like you and have that discipline?
It's I always feel that I spend too much time doing it because I've always got things that I want to achieve during the day, and usually it's writing an article or at the moment, I'm trying to get my head around some legal stuff that I'm involved with in terms of acting on behalf of I won't say what it's about, but it's astronomy related, legal issues. So that's the kind of thing that I should be really getting onto, but my head really wants to soak in what's coming out in the science news. So sometimes it's an hour in the morning that I spend delving into these stories, because you see a headline, and especially when I've spent my entire life working in this field, so it's stuff that has basically been second nature to me. So quite often I'll see a headline and think, but wait a minute, if that's the case, then this mustn't be right, and that mustn't be right, and that sucks me in straight away. It's like clickbait almost, and it works perfectly for me because it raises. I see a headline, it immediately raises questions. So yeah, I've got to look at that story. So yes, it's probably, as I said, it's part of the morning routine. I would say typically half an hour, but often it's more like an hour, and sometimes all morning if there's really interesting stuff going on.
Well, thank you for sharing your all the knowledge with us.
Oh, well, yes, it's all secondhand knowledge. Well, a lot of it is. Some of it is stuff I've worked on myself, but a lot of what I do is really, in a sense, it's my way of paying homage to these fabulous scientists who are working around the world on stuff that's very close to my heart and yours too, Heidi, in space research and astronomy. So it's a great way to perhaps give back to those researchers a little bit of the kudos that they deserve on a wider platform, which is, I guess, what Space Nuts is.
Yeah. I mean, that's how I originally found the podcast, is I just wanted a different medium to start learning more about space, and here we are.
And there you are. Yeah, you definitely got sucked in, Heidi.
I got sucked in. Your orbit was strong. All right, everybody. Well, this has been another wonderful episode. Thank you so much for tuning in. Please keep your amazing questions coming. You guys really are half the show, and we appreciate you, and we look forward to these questions every week. With that being said, I have nothing else to say. Fred, do you want to sign us off?
Yeah, just keep an eye on what's going on. Space astronomy is looking up, as we all say, and it's true certainly of space science as well. So keep on looking up, keep on tuning into Space Nuts, and we'll catch you next time.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.